Hello everyone, thank you for joining today. And I'm Olivier Bernard. I'm currently a researcher at SAMA, and I'm going to present you today our latest work with Marc Joie about bootstrapping TFHE ciphertext via automorphisms, and the subtitle is Closing the Gap Between Binary and Gaussian Keys. So first, a little summary of what the key contributions, what I'm going to present today. So the presentation is about automorphism-based bootstrapping. We are going to present a novel traversal blind rotation algorithm that is optimizing the number of key switches, which is the main problems currently for automorphism-based methods. And also we derive from that a new automorphism-parametrized external product that removes the automorphism key switches, that meaning that from an encryption of M1 and a special encryption of M2, you could directly compute the encryption of psi of M1 times M2, this one here, with for the same cost as you would have paid for computing the encryption of M1 times M2. So if you combine this traversal framework with a new automorphism-parametrized external product, you obtain what we called an automorphism-parametrized blind rotation, which gives very efficient trade-offs between the key sizes, the bootstrapping key sizes, and the performance and noise growth, and both are really kind of directly linked. So when I talk about performance, I also talk generally about noise growth. If I may jump ahead a bit, this means that there is almost a 50% reduction in the number of key switches with a similar key material as proposal by LLW Plus in CHESS 2024. And it also allows to remove almost all the key switches with only a moderate increase in the key material, meaning it's 9 times overhead. But it's still a lot less than what would be the state of the art, which is probably 1,000 times increase. And we also provide, last but not least, a theoretical framework that is aligning well with experimental results. And this 99% reduction in the number of key switches is really what we mean when we are saying that we are trying to close the gap between binary and Gaussian keys, and I'm going to explain that right away. So so for bootstrapping ciphertext in few crypto systems, there are currently 2 competing main branches that are AP and GINX from the eponymous paper. And I will start with AP because it might be the simpler to understand at first sight. And so the idea is always the goal, sorry, is always the same. You have as input LWE ciphertext, which is a 1 to A and B, and B is the combination of the mask and the secret plus the message plus some error. And you want to output the LWE ciphertext that is encrypting some, okay, this is a constant thing that we don't need to worry about. And the main thing that we want to compute is this, what we call the blind rotation. It's computing this inner product A times S in the exponent of X. And how do you do that? So it's always the same principle. You start by an accumulator. You initialize this to 0, 0, 0, 0, and the body will be just V times X minus B, and this is a trivial encryption of V times X minus B, meaning that the mask A here is going to be 0, and the error is also going to be 0. So there is no security at all, but everything is public yet. And then you iterate on the LWE masks, A1, then A2, and so on. And each time you compute an external product. I will define this later, but the external product is just an encrypted version of the multiplication. So you start from an encryption of v to the x minus b, and then you multiply by what's inside here, x to the ai si. And so you see that at the end, you should have an encryption of this thing, because you start from v, then x minus b, then you have x minus b plus a1 s1, and then a2 s2, and so on. So you could do a simple induction proof that at the end you already have an encryption of this thing. And then you can see that, okay, in that case, you have no restriction of what is going to be the SI here. You have no restriction on this value because it's x to the SI, and it's always the same size. So homomorphically, this is not going to be a problem. But then you need what we call blind rotation keys, which are these big things, JWE, extended JWE ciphertext, for each possible value of AI, which means that at the end you have 2 big N, which is typically 2048, times the small n, which is also a few thousand, let's say 800, a few hundred, sorry, 800, extended JWE ciphertext. And on the other hand, there is this GINX branch that has the same structure. So you have always this, there is also this initialization step with the trivial ciphertext of v times x to the minus b. And then the GINX method imposes that the secret key for the LWE ciphertext is binary. So it's 0 or 1 each time. And so inside the loop, you have this famous CMUX, homomorphic CMUX evaluation. So the first step is to multiply the accumulator by x to the ai minus 1. And then you apply the homomorphic external product by 0 or 1. So if it's 0, you obtain 0 overall, an encryption of 0, a complicated encryption of 0. And then you add the accumulator. So the accumulator stays the same, which is expected, because if SI is 0, then there is nothing to do. And if SI is 1, then you have this thing that is multiplied by 1. And so at the end, you have x to the ai times what was encrypted in the accumulator, which is the right update for your ciphertext. And so you can see that then you only have to encrypt you only have to encrypt the L components of the LWE key. And so you have small n extended LWE ciphertext. So the bootstrapping keys are as small as they could be, I guess. And but then you have to use binary LWE keys. And that might be a problem. I mean, I'm not claiming there is an attack on binary LWEs. There is not, but it's another attack avenue that could be. I mean, if we could avoid using binary keys for the same performances, that could be great. And both methods have the same computational and noise performances, because you can see that essentially you have n external products in each case. And so, so the problem is binary keys versus Gaussian keys on the right, and but you have small blind rotation keys for binary keys, and you have too huge to be practical keys for Gaussian keys. Okay, so I'm going to define properly what is the external product, and we are going to define another homomorphic operation, which is automorphism, which is going to be used a lot in this talk. And then we are going to see how we can transform iteratively AP to obtain something, a nice blind rotation algorithm using automorphism. So okay, about homomorphic operation. So the main operation that we are the main, it's also the costliest. It's the external product, and it allows you to compute from yeah, you have a ciphertext encrypting new and another ciphertext encrypting new bar, and then the external product allows you to compute this thing. And for this, you need auxiliary ciphertext. So the first thing to enable is the multiplication by some arbitrary elements. So you want to be able to compute the encryption of A times mu when A is a bit constant. And if you do that naively, then you will blow up the noise because, yeah, the noise will also be multiplied by A. And then, yeah, you will just destroy your message. So for this, there is you need to define a gadget decomposition associated to some gadget vector. And essentially, the idea is that you take your big element A or polynomial A, and then you decompose it into a vector of small integers, so that when you combine the decomposition of this A by with the corresponding elements of the gadget vectors, then you obtain a close approximation of the original element. So you don't need to know the specific of the gadget decomposition. You just have to remember there is a gadget decomposition, and that it allows you to essentially multiply by arbitrary elements. How do you do that? So you define a gadget GLWE encryption, which is essentially translated version of the message. So you have encryption of translated version of the message by some by the gadget vector components, and then this allows you to combine the decomposition of A by the gadget GLWE encryption, so that if you look into the detail, you have the sum of this. Each component is multiplied by the corresponding encryption, translating encryption by GI. So if you include that, so this is going to be a GLW encryption of the one element of the decomposition A times GI times mu. And if you sum all of these inside this, you will obtain something that is close to A times mu, and the fact that it's close to A is going to the error. So at the end, you only have to to remember that the gadget GLWE encryption allows you to decompose an element, combine this, and then you obtain an encryption of this. So you to compute scalar multiplication homomorphically by public elements. And actually, the external product is trying to compute an homomorphic multiplication by a private element. And for this, you need an extended GLWE, which is a set of gadget GLWE encryptions. And then here you also translate the message you want to encrypt by the component of the key. And so the external product is a collection of k plus one, sum of k plus one scalar products. And if you look at this formula, so you will have inside this will give you an GLWE encryption of B times the mu bar. And each of these is going to be an encryption of AJ times minus AJ times mu bar. And then if you factorize everything, you will obtain B minus the sum of SJ, AJ times mu bar, which is mu times mu bar. And so, yeah, you can forget now about all the technicalities in this slide. You just, yeah, there is just this external product, which is a collection of k plus one scalar products. And this allows you to compute the multiplication homomorphically between two encrypted elements. And one of them is a big encryption. It's a special one. Okay. So now I will move to automorphisms. And one thing I didn't mention purposely is that actually the elements of GLWE ciphertext are polynomials, and they live in this kind of ring where big N is the power of 2. This is not really important, but this has the importance is because then there is the existence of these special maps here for any integer u that is invertible modulo 2n. So the map is effectively sending x to the u, and then you could verify if you are, you could verify that psi of a plus b is indeed the sum of psi of I and psi of b, and that the psi of a times b inside this ring is also the multiplication of psi of I times psi of b. And that means that if you apply psi on each of the components of a GLWE ciphertext, then you will obtain something that is homomorphically meaningful, which would be a ciphertext of psi of mu, but under a new key psi of s. This is because psi of b is going to be the sum of psi of I times psi of si, and this is where the psi of s comes from. And so you have psi of mu, which is what you want. Psi of e is going to be an error which has the same amplitude of the original error. And so there is only this problem that the key has changed in the meantime. So this yields an homomorphic evaluation of automorphisms. And essentially, the idea is to apply psi of each of the components, and then you fix the problem of the key by using a key switching operation from psi of s back to s. And the way that the key switching is working is also using gadget decomposition. And you can see that it's almost like an external product, but instead you do not do an homomorphic multiplication of psi of beta by an extended GLWE ciphertext of 1, because it's just multiplying by 1. You don't need to have a complicated product for that. But so okay, so you can see that key switch is almost as costly as an external product actually, and this is also the case for the noise, maybe the same proportion roughly. Okay, and so if you apply this operation, you can see that at the end you obtain GLWE ciphertext of psi of mu under the correct key. Okay, and so this is the set of these values. Yep. The gadget GLWE encryption of minus psi of Sj is called the automorphism key. So generally, I'm going to talk about the automorphism key, and there is, and the thing to remember here is that there are automorphisms, and you can homomorphically evaluate an automorphism by using a key switching from the image of the key back to the original key. And so the homomorphic evaluation of automorphism is really equivalent in some sense to the key switching operation that is beneath. Okay, so now that we have defined briefly these two operations, how are we going to use that for AP blind rotation? So maybe, so AP blind rotation is here. There is initialization step, and then each time you do external product by some GLWE of x to the AI si. Okay. So now the idea is, so in this slide, I'm going to adapt progressively the AP blind rotation to go to a new framework that we propose. And the idea of these slides is there is some technical details on the right, and if you don't want to go into the technical details, there is I try to do some summary, high-level summary on the left, so you can focus on this part. Okay. So the first reference I found, I think, for the automorphism-based AP blind rotation is from BDF 18. And the idea is rather, not simple, but so you start from AP blind rotation, and inside the loop we add this line, this homomorphic multiplication by a GLWE encryption of x to the AISI, and we are going to replace this by first applying some kind of normalization automorphism by 1 over AI, So yeah, I'm going to divide everything. So if the accumulator was encrypting P of X, so after this operation, it encrypts P of X to the 1 over AI. Then you perform an external product with X to the SI. So then the encrypted value, the message that is encrypted is X to the SI times P of X to the 1 over AI. And then you denormalize everything by applying to AI, to X to the AI. And so then the message that is encrypted is X to the AI SI times P of X, which is exactly what we wanted in the first place. So this is completely equivalent, but now you have much smaller keys because you only need the bootstrapping keys for X to the SI. You don't need to deal with all the masks. And but you also have automorphism keys for every possible automorphism you are going to apply. So that means that you have n plus big N extended GLWE ciphertext, or phi, instead on big N times N. So you have much smaller keys, which is good. But the downside is that now it's at least twice as costly or noisy because, because you have two automorphism key switches to perform there. And remember that key switch is depending on the number of components here, depending on the number of the K here. So if K equal 1, it's at least 1/2 of an external product. So 2 is going to be, so yeah, overall it's twice as costly or noisy. And you may notice that if you unroll the loop, then you have this automorphism that is directly combined with the next. And this is what we call the telescoping method. And this trick has been, I mean, it appears in several papers. I listed 2 of them, but certainly it appears in other places. I don't really know. I mean, this is not the main result of those papers, but the trick is appearing there. So the general idea is just to merge both sides of the loop. And this way, because when you just compose 2 automorphisms, then you can express this as a single automorphism. So yeah, in formal terms, you could say that the automorphism is a group. The set of automorphism is a group. And so this gives this algorithm, and I take this opportunity to introduce what I call the state of the accumulator, the automorphism state of the accumulator. It's an integer that encodes the automorphism state of the accumulator, meaning that the accumulator always encrypts P of X to the 1 over this state. And this is I think a good way of thinking of it, because then at the end you want the state to be 1, and in the meantime you just have to keep track of what is the state to not do random things. So here you start with the state which is 1, and then the merging is going to be, you want to go to state 1 over AI. And so whatever you were, so you were in the 1 over A old state, and you want to jump to 1 over AI. And so the automorphism you are going to apply is the quotient of the 2. So this one. And this is a completely equivalent way of writing, just merging the automorphism when possible. And you can see that here you will always encrypt X to the P of X to the 1 over AI, because you were at the state 1 over A old, and you just multiply by this, so you obtain the X to the 1 over AI. And there is, at the end, maybe you didn't reach state 1, if an is not equal to 1, for example. And so you have this finalization step to apply. You have to apply the last automorphism to get to U equal, yeah, to obtain an encryption of this one without an automorphism. So the good thing about this is that now you have twice less automorphism key switches from 2n to n. And but yeah, it's still at least 1.5 times more costly and noisy than AP or GINX. Okay. Another remark. Okay, let me go to next slide. So you may have noticed that if the automorphism you have to apply is 1, like here. So if it's 1, then this step is completely free. You don't have to do anything because there is no automorphism to apply. So it seems natural to at least order the mask value so that you treat them in batches. And there is also a better thing that was suggested by these people, LMK plus, in 2023. And this is a rewriting of what they proposed, but the big idea is to sort not only the mask values, but also by discrete logarithms, using the group structure of the automorphism set. So, and the automorphism set is this one, and the group structure is just you have a sign, plus or minus 1, times a cyclic group that is always generated by 5, by G equal 5. I mean, at least if this big N is big enough, which is always the case. And so you can also, so you can iterate on the group structure directly. So they propose to start from the sign, -1, then +1, and then treat the cyclic components inside the loop. And so yeah, this set IT epsilon is going to just encode the set of indexes that have the same value, basically. And so the algorithm is going quite the same as before, but using the group structure to order the masks. And so you have the same thing. You have to jump from G to the T all to G over T. And the way it's computing is just a subtraction between the correct one. And when the set is empty, you don't have to do anything. And the other great idea of this this paper is about how you fill the gaps. So this is another terminology I would like to introduce. So when you have a non-empty set, yeah, you have to fill the gap between your old state and your new state, automorphism state. And this is what I call the gap. And for filling the gap, you can jump from one to another using an automorphism key switches. And maybe the gap is too large, so that you would need too many automorphism keys. So that they propose to actually factorize these gaps by using a window of size W and rewriting the G to the delta by G to the W, etc. times G to the rest, whatever is left to do. And then you can see that you only need automorphism keys here. Well, sorry. You only need the automorphism keys for a limited set of automorphisms, 2-1 to G into G to the W, which is great because then you don't need 2,000, 1,000 automorphism keys, but maybe just 20 of them. So you have a reduced key material. And the fact is that the number of key switches converges quite fast to the number of distinct values in the mask, in the LWE masks. So W is rather small in practice. Like I said, around 20 would be a good value already. Yeah, I didn't mention that between the two loops, you have to apply this complex conjugation to invert the sign, and then okay. And so you can see that if you had an infinity size for the window, then you will still have to do at least as many key switches, automorphism key switches, as you have distinct values. And the other thing is that the gaps are quite big because you choose n values and masks amongst big N possibilities, and so you generally have kind of bigger gaps. Okay, and this leads to the what we call the traversal method. Okay, in the slide. And so we notice indeed that often you have both sets plus or minus that are both empty, and that means that you have to go over them for each side of the loop. So when epsilon is -1, you go over it because it's empty, and then when epsilon is +1, you also go over it because the set's empty, and you could just go past them in one time. So the general idea is just to invert both loops. Yeah, and why is it more efficient? It's because then the gaps are going to be smaller, and you can include sign changes on the fly using symmetric automorphism keys. So the automorphism key is now going to be t tau -1, tau ± g, and tau ± g to the w/2. So you have the same amount of other automorphism keys, but the fact that you inverse both loops means that it's going to be a bit more efficient, and you will have less key switches in general, and yeah. And the fact is, it's a bit cleaner to analyze because you don't have this complex conjugation between the two loops that is sometimes cutting your thing into. So yeah, it's just a bit cleaner to analyze, and this is not really an improvement in terms of performance and noise because if your window is big enough, they are both converging to the same number of distinct values, and this is because, yeah, when both sets are non-empty, you still have to apply a complex conjugation to go from one to the other. So this is what I call zero size gaps with sign change. So, and the question is, can we go further? Can we go beyond this limit of the number of distinct values in terms of key switches, automorphism key switches? And this is where we introduce automorphism-parametrized external product. So for this new operation, you need a new auxiliary ciphertext format, which we call the automorphism extended GLW, and it allows to combine an automorphism inside the extended GLWE ciphertext. So if psi is equal to the identity, this is the same as before, but the fact that you have psi of s and psi of s here allows one to compute directly an automorphism on the message and the multiplication with another encryption. So this is really what it does. So how does it work? You have on one side a GLW encryption of mu. On the other side, you have this new automorphism parameterized encryption of mu bar. And then one needs to apply psi on each of the components of this message. And then the formula is the same, I think. Yeah, it's the same as the one of the external product, but using this new key. And you can see that then you have an encryption of psi of mu under psi of s. And since you combine with encryption with psi of s. At the end, you obtain an encryption under s of psi of mu times mu bar. And so you obtain in one step, you obtain an encryption of psi of mu times mu bar. So the real point is that there is no more automorphism key switch that you need. And this is exactly the same performance and noise as the classical external product. And also as a side result, it's also applicable to N-true or any auxiliary encryption that allows you to define an external product. So how are you going to leverage this new external product inside our traversal framework? The point is, so you start from the traversal method, you define a fixed set of automorphism. For example, you could consider the identity and the power of G, or plus minus 1, plus minus G to the K. So you have as many automorphism extended keys as you have elements in S. And you also need automorphism keys to treat the remaining gaps for window size, which is going to be intuitively what it was before, minus the maximum value that you could address using the automorphism extended external product. And the idea is quite simple, I would say. It's about a new jumping strategy where you are using automorphism key switches only to find the shortest path to your special set of automorphism. And then the first external product that you are going to apply is effectively a new automorphism-parametrized external product that will allow you to go to the state that you want to go to. And it will close the gap effectively. So yeah, it's 2 steps: automorphism key switches for the shortest path to S, and then new external product. And then if there are still remaining elements in the set here, you just use regular external products to finish the job. And the important point here is that actually the new external product is modifying the automorphism state of the accumulator. And so this gives very efficient trade-offs. And the number of key switches can go as, can converge to constant, on average, number of key switches with the size of S. And this is, for example, K, big K equals 8 will be sufficient to get on average two key switches. I wanted to make a quick comparison with related works. So I mentioned already LLW+, and there are also, so LLW+ is gaining all complex conjugations because they are using extended GLW encryption of x to the plus minus SI. And this allows you to handle all the sign changes in just without changing your state. And this is already almost 18% of the key switches. And the second method is looking at what happens when K increases. And it's called adaptive key updates, and the technique really boils down to increasing the K here. And the thing is that these methods allows one to look forward. When you are at one automorphism state, you can just treat further things that you see, but it's not moving the state forward. And so as a consequence, you still have many key switches that may remain even for small gaps if the things are not well aligned with the state where you are, or the last sequences of zeros and so on. And also there is little side effect. There is no common term inside these keys. They're all different, so you cannot factorize so you have slightly bigger keys. Yeah, in the new automorphism standard ciphertext, yeah, there is one value that is common that you can reuse from one key to another. Okay. Just a quick word about the theoretical analysis. If you see the thing like this, so with the traversal framework, at the end, it's just about studying the distribution of the gaps when you choose small n values amongst big N over 2. So this is what is called the random cut of an interval, and a lot of the work has been done by a mathematician called Darling in 1953. In the discrete case, you have to center a bit the interval. So, a naive way of doing this would be to just think about t minus 1/2 and t plus 1/2, just centering the interval. This gives values that are quite off the reality, and there is a reason. It's because there is a little less sign changes than 1/2. So the offset might be of this form, and then you obtain the average number of gaps, which has this this kind of form. Yeah, and this allows us to derive a theorem about the average number of automorphism key switches in our S-parametrized blind rotation. We also have numbers for the telescoping method and so on. And this average number of key switches is going to converge to some kind of number of distinct value. I mean, yeah, some kind of constant once you fix the n and big N times a decreasing constant. And this means that each time you increase k by 1, then you multiply the number of average key switches by this thing. And other side effects, the fact that you have a closed formula, it was also formally defining an optimal window value, so that the average number of key switch that you could expect using this optimal value is not going to exceed the best one by more than alpha. And typically, I think we took alpha around 0.20. Yeah, something like that. Just before we conclude, I have this table with some performance measurements, and there are a few things that I want to highlight. So there is this LMK plus 23, which is almost as optimal as it could be in terms of key sizes, but you have 700 key switches to perform on average. And there is this LLW plus generalization that is using x plus minus SI, that is thus doubling the size of the keys and removing all the complex conjugations. So there are 117 of them. And we will compare to LLW plus here in this talk. And the first thing I would like to present is, if you use this asymmetric set ID to G, so you are ignoring the complex conjugation. You are not going to treat the complex conjugation using the new automorphism star product. Then you have 25% less keys, but you still get more. You still remove more key switches. So you have 30% less key switches for 25% less keys. And this is because you can see this graph that actually the number of gaps of size 1 here is a lot bigger. So it's a lot more interesting to treat the gaps of size 1 than treating half of the gap of size 0. So the complex conjugation I'll show you here. Yeah, 220. And so it's a lot more interesting to treat the gaps of size 1 than the gap of size 0. And this is exactly what we see here. And the second thing that we would like to see, if you if you want to treat all the gaps of size 1, not just the positive one, then you have the same amount of keys and you further reduce the number of key switches. So you have 35% less key switches at LLW plus 24 than for the same amount of bootstrapping key for n plus 10. And the last thing that is worth noting is that there is indeed when you increase k, each time you divide the number of key switch by 2.25, which is a lot. And this is why at the end, if you have a 19 and GLWE, extended GLWE keys, you have on average two key switches. And all of this is extremely close to the theoretical prediction. Okay, so I think I've finished the talk. So yeah, just as a summary, I presented a new automorphism parametrized external product and associated blind rotation, and this gives very efficient trade-offs between the bootstrapping key size and the number of key switches that you have to apply. This gives better performances than the state of the art, and maybe the most important thing is that it allows to get to a constant number of key switches with a really moderate increase in the key sizes. And the last motivation is that if you have Gaussian keys, you could eventually decrease the LWE dimension by maybe 10 or 15%, and this should give directly an increase in performance. And also presented a theoretical analysis that gives a closed formula for the number of key switch, and I think this is really important to get meaningful parameters in general, and this has been validated by numerical experiments. And if you want to look at the full paper, it's only printed at this number 25/163, and yeah, thank you, and don't hesitate if you have any questions. I'm also available by mail at this address with .bernard@zama.ai. Thank you.